Last time we were talking about how the neuron works. The neuron works by exchanging ions between the outside of the neuron and the inside. The outside is has mostly sodium on the outside. It has potassium on the inside. The three most important chemicals that we're talking about are sodium, potassium, and chloride. Now, if you understand salt, then you recognize the fact that this represents salt. There's potassium salt and there's sodium salt. Most of the salt that we consume is sodium salt. So salt is extremely important. Where does salt come from? Well, if we look at the oceans, we can see that the ocean is made up of salt, as weird as that is. So if we determined how much salt there was in the oceans, and then we looked at how much salt there is in our own systems, what we would discover is there's exactly the same amount. As weird as that sounds. So salt is the essence of humanity, I guess. They did a Star Trek episode one time where an animal would suck all the salt out of a human being in order to survive. That was how they ate. They ate salt. It's kind of a strange episode. When the neuron is stimulated by a neurotransmitter detected by a dendrite, the chemical neurotransmitter causes localized depolarization. In other words, the neurotransmitter causes sodium channels to open in the immediate area. The sodium channels open, and the sodium comes rushing in, creating a more positive atmosphere. Sodium ions are a little bit bigger than potassium ions. For a neuron to react, it must receive an adequate amount of neurotransmitter to stimulate enough sodium channels to open up. This is known as its threshold. Usually depolarizes at negative 50 millivolts. If the threshold is reached, then enough sodium channels will open to trigger the depolarization. We've got all the sodium rushing in. We have some potassium rushing out. And now all of a sudden we have a positive neuron, and that is the electrical charge that we're talking about. Normally it's negative on the inside. A neuron cannot partially fire. It either fires or it doesn't, and this is known as the all or nothing property. So if you smash your finger, there is an immediate amount of pain. Later on, you may realize that the pain that you felt was not didn't equal the amount of damage being done to your finger, and this is because when the neurons fire, they fire all the way, telling you, "Ouch! There's a pain right there." When the threshold is met, sodium ions flood into the portion of the cell through the rapidly opening sodium channels. So we're talking about sodium channels, and in a minute we're going to talk about potassium channels, the neuron going back to its threshold, going back to normal, in which case the potassium channels will open up, replacing the sodium with potassium. And since the potassium ions are much smaller than the sodium ions, of course the positive charge will change. This triggers the sodium channels next to the stimulated area to depolarize as well, causing a chain reaction along the neuron until it reaches the neuron's own synaptic cleft. At that point, the electrical charge will stimulate calcium channels, and the calcium channels it'll increase the amount of calcium, and then that will cause the synaptic cleft to the vesicles to open up and release the neurotransmitter. Let's see if I can get this neuron resting potential thing taken care of. I don't know if I have online access. I was having trouble with this earlier, and there it goes. It's not working. Working on my computer, it's not working.
Unstimulated, neurons maintain a constant...
I'm sorry. Okay, yeah, well, it was working. Works on my computer, but you guys can't see it. Wait a second. There we go. Action potential refers to the amount of positive ions that are allowed to flood into the stimulated area of the cell through the sodium channels before the sodium channels close. The action potential for most neurons is positive 40 millivolts. So we got a negative charge. We got a charge of somewhere between negative 50 and negative 70 millivolts. We have the sodium rushing in, and it rushes in to the extent that it doesn't go to a point of 0. It goes to a point of positive 40 millivolts. And at that point, they close. Going beyond equilibrium with the outside environment, 0 millivolts, is called the overshoot phase. So it's kind of like if you're trying to carry a bucket of water and the water is sloshing around, you're trying to keep it into the bucket, but there's so much sloshing that some of it comes out the side. Well, that's the overshoot. That's you overshooting. Trying to carry your bucket of water, it just sloshes out. So that's the overshoot phase, and the overshoot phase goes up to positive 40. Remember, we need to go back down to negative 70 to be at the threshold, at the action potential, at the point where it can fire again. It can't fire at positive 40 because the electrical charge is positive. It needs to be at a negative. The inside of the neuron has to be negative in order for it to fire again. And we've just gone all the way up to positive 40, and this is known as the overshoot phase. While a neuron is recovering from stimulation, it cannot be stimulated, and of course this is known as a refractory phase. Refractory means it won't work, it won't function. We talk about refractory in other aspects of medicine, but this is the refractory phase of the neuron. During the refractory phase, the sodium channels are closed, shutting off the supply of sodium ions flooding into the neuron, and potassium channels open. They open to replace the sodium with potassium. So the potassium starts coming in. Because the electrical charge outside the cell is more negative than inside the cell, the potassium ions are drawn out of the cell. And when they are drawn out of the cell, of course, it becomes more negative. With the positive potassium ions now flooding out of the cell quickly, now you have to remember that the sodium ions and the potassium ions are not the same size. Sodium ions are much bigger, potassium ions are much smaller. So when they go flooding out, the sodium cannot go through the potassium channels, and the potassium can go out the sodium channels, but at this stage, we only have potassium going out. We don't have any sodium going out. It goes flooding out of the cell. The cell quickly loses its positive charge, and it not only reaches its resting phase potential, but it goes beyond it in a phase known as the undershoot phase. So it actually becomes more negative than it will be able to fire. The potassium leak channels now allow enough potassium ions to re-enter the cell to return the area to its resting potential. And that's because it becomes too negative. Neuron dendrites and somas usually have a different type of membrane than axons do. Dendrites and somas usually have sodium channels that are stimulated by chemicals and not by voltage. In other words, they are only activated when the chemical neurotransmitter is present. So it's a chemical reaction. It has to be, the neurotransmitter has to be there. The chemical has to be there in order to trigger the neuron. If it isn't there, then it won't trigger. It has to have this chemical. And then, of course, it creates an electrical charge. So it's a chemical electro reaction. Actually, they call it electrochemical reaction because there's an electrical reaction to the chemical. The axon, on the other hand, does have voltage-gated sodium channels. So the axon responds to stimulation from the dendrite and the soma. So the axon is actually electrically stimulated, whereas the soma and the dendrites are only chemically stimulated. The neurons in the central nervous system are myelinated by oligodendrocytes, and the neurons in the peripheral nervous system are myelinated by Schwann cells. The myelin covering the neuron does not allow potassium leakage from the area covered by the myelin, and that's one of the reasons why the myelin is there, to keep the potassium leakage from occurring. And because of this, of course, it accelerates the reaction. The depolarization voltage is channeled down the axon from one node of Ranvier to the next, increasing the response by as much as 15 times. So a myelinated neuron is much more, reacts much more rapidly than a non-myelinated cell. This form of conduction is known as saltatory conduction. It accelerates the whole process. If we look at the spinal column, what we see is white matter on the outside and we have gray matter on the inside. If we look at the brain has gray matter on the outside and white matter on the inside. The more gray matter you have, the more intelligent you are. But when we're talking about information moving from one place to another, that's mostly in the white matter, the myelinated matter. The spinal column, on the other hand, you need to react very quickly, so the white matter is on the outside to accelerate that process. Multiple sclerosis is an autoimmune disease where, due to a genetic flaw, environmental trigger, an individual's immune system destroys the myelin on select neurons. This is kind of a serious situation in that, as you can see, the myelin has been destroyed, and because of that we get more potassium leakage. Because we get more potassium leakage, the reaction is much more slow, is much slower, and so where normally you can react very quickly, in the case of multiple sclerosis you not only can't react quickly, but eventually it will create a situation that is of paralysis, where that muscle, that neuron group will stop functioning completely. This causes slowing of the movements and loss of sensory abilities due to the slowing of the neuronal response. So what we're dealing with here, this is a peripheral nervous system, so we're dealing with Schwann cells. Most synapses are triggered by a chemical neurotransmitter in the synaptic cleft. But researchers have discovered that some synapses in the brain are stimulated by electrical responses from another neuron. So it's not a chemical reaction, it's an electrical reaction. There aren't that many of these in the brain. Most of them are triggered by chemicals, by neurotransmitters. We're going to talk about some of those neurotransmitters in a minute. A lot of times the neurotransmitters have to do with emotions, with feelings, and because of that, of course, we can control, potentially we can control your behavior by increasing or decreasing select neurotransmitters. For example, if you feel anxious, if you feel anxiety, one of the things about anxiety is that it's created by a lack of gamma-aminobutyric acid, GABA. GABA, if we can increase your GABA level, we can take away your anxiety, and that's one of the ways that we treat it. We increase your GABA level. Depression is caused by a lot of different chemicals, but one of the chemicals that we can increase to make you less depressed is serotonin. So we will give you a medication such as Prozac, which increases your serotonin level in your synapse, and if you have more serotonin in your synapse, you're less likely to be depressed. So we can do that. If you have schizophrenia, one of the reactions that you have if you suffer from schizophrenia is that you have too many dopamine receptor sites, D2 receptor sites. There's actually 5 different receptor sites, D1 through D5. But it's the D2 sites that cause the problem. So if you have schizophrenia, then you have too many dopamine receptor sites. So one of the things that we can do is give you a medication that will block those dopamine receptor sites. But if we give you too much of that medication, then what will happen is that you will start having Parkinsonian symptoms. In other words, you'll start moving and reacting as if you had Parkinson's disease, because Parkinson's disease is caused by a decrease of dopamine in your brain due to degeneration of your substantia nigra. It's an area that produces dopamine. So schizophrenia is caused by too much dopamine, and Parkinson's disease is caused by too little dopamine, as weird as that may sound. Alzheimer's disease is caused by a decrease in the death of the cells that produce acetylcholine. Acetylcholine, of course, is the neurotransmitter that transfers information from your short-term memory to your long-term memory. So you have a difficult time remembering things. Your short-term memory is decreased. As weird as that is. And this is what a chemical synapse looks like. A chemical synapse, normally a synapse is relatively large. It's between 20 and 40 nanometers, but one of these is only 2 to 4 nanometers between the two. So an electrical charge can jump over this one. The other one is so large that they can't jump. The electrical charge can't jump, and that's why you need chemicals to induce the other neuron to fire. Not all neurons cause their connecting neuron to fire. Some neurons are inhibitory neurons, and instead of raising the excitatory potential, depolarizing the neuron, it lowers the excitatory potential, it hyperpolarizes the neuron, making it more difficult for the neuron to fire. So how in the world does it do this? It does this, inhibition is done by inducing channels in the receiving neuron to open, allowing more negative chloride ions into the neuron. And since it makes it more negative, it takes more stimulation in order to get this neuron to fire. Okay. It lowers the neuron potential to fire. An inhibitory or excitatory neuron is determined by the neurotransmitter that they produce. A good example is GABA. GABA, almost all the glutamates are inhibitory. Serotonin is sometimes excitatory, but it's normally an inhibitory neurotransmitter. So acetylcholine is the same way. In some situations it's an excitatory, in other situations with select neurons it's inhibitory. And I'll show you an example of that in just a second. Some of the neurons have hundreds of other neurons feeding into them. With these neurons, they may require a number of neuronal stimulations before their threshold is reached. This accumulative effect that is required for stimulation is known as spatial summation. Spatial just means space. It takes a certain amount of space. As you can see, a certain number of neurons have to fire. It goes over a certain distance, and because of that, it's a spatial summation. It takes a certain number of stimulations to get that neuron to fire. If I seem a little hesitant today, it's because I've been talking to an empty room. It's not easy for me to do this, but I guess I'll get through the lecture. I do feel like I'm hesitating. It's a lot easier when I'm talking to somebody, but No one has showed up for this class. There's usually only a couple of people in this class. So that's the way it is. Some neurons that require an increased threshold will not react from a single neuron stimulation. However, if the single neuron fires in rapid succession, the cumulative effect of the neuronal stimulation will stimulate the neuron to fire. And of course, it just takes a select amount of stimulation. So whether it comes from one neuron or 100 neurons, it still takes that much stimulation in order to get the thing to fire, to get your neuron to fire. Because it is a matter of adequate stimulation in a select time period, this type of stimulation is called temporal stimulation. Temporal merely means time. So there needs to be a select amount of stimulation over a select period of time. And if one of them fires, but it fires very rapidly, it has, I don't know, 15 nanoseconds in order to get this thing to fire. If it doesn't stimulate it enough in 15 nanoseconds, then it doesn't fire at all. Since a threshold has to be achieved before a neuron will be stimulated, there are various structural factors that can increase the likelihood that a neuron will be stimulated. The number of dendrites receiving stimulation increases the probability that the threshold will be reached. If a glial cell overlaps the synaptic terminal, it may increase the amount of neurotransmitter in the cleft by not allowing any leakage. And of course, it takes a certain amount of stimulation. That stimulation comes with a neurotransmitter. If there is a glial cell that's holding all that neurotransmitter in, none of it can leak out. Of course, it's just a chemical, so it's flowing from one place to another. It doesn't have to go from one place to another. It can go anywhere. It can just go into the synaptic cleft. So what you may have, if you think about it, we have select families that seem to have a genetic proclivity for depression, for example. Well, their problem could be manyfold. One of their problems could be that they're not producing enough serotonin. How do you increase your serotonin level? Well, there's lots of different ways to do it. You can take Prozac, of course, but if you want to do it naturally, exercise, of course, will increase your serotonin level. One of the other problems could be that their neurons the synaptic cleft is wider apart. And since it's the neurons that control your depression are in a certain portion of your brain, if those neurons are farther apart, then you have to pump out a lot more serotonin in order to get it to fire the next neuron, as you can see. So, there could be lots and lots of different reasons why somebody's depressed. One of them could be that they don't exercise enough. Just laughing will increase your serotonin level. As weird as that may seem. A chemical synapse works in the following manner. The electrical charge travels down the axon to the axon terminal. The charge changes the permeability of the calcium channels, allowing calcium to enter the synaptic terminal. The calcium causes the synaptic vesicles to fuse with the terminal membrane, releasing the chemical neurotransmitter contained in the vesicles into the synaptic cleft. So the four chemicals that you need, or the four elements that you need in order to have a normally functioning body, is sodium, of course, potassium chloride. Of course, potassium chloride or sodium chloride comes in salt. But the other one is calcium. And if you don't have enough calcium in your system, then potentially your neurotransmitters will not be able to be activated. So calcium, sodium, potassium, and chloride are four of the major elements that you need in your system. So you need to take in salt, of course. If you don't take in enough salt, now you've got a kind of a serious problem. Some people will dilute out, I think I talked about this last time, Some people will dilute out their sodium, their salt content in their body by drinking too much water. That's called hypernatremia, where you take in too much water. And these individuals have a really serious problem. They don't have enough sodium in their system. It dilutes out their sodium. So if it takes out sodium, they don't have enough sodium in their brains to fire properly, and they start acting erratically, as weird as it may seem. If you don't have, if you have salt in your system, but you don't have enough calcium in your system, calcium is not all that obvious in your brain. Of course, you're not thinking quite clearly. You've burned off a lot of your calcium. I was reading a book the other day. They were talking about the fact that this lady had she started having tumors in her brain, and so from that she determined all these other various things. She exercised a lot. She was exercised quite a bit. And she always said that after she exercised, she wasn't very smart. She was a neurosurgeon, and she said that she couldn't operate unless she hadn't exercised for a number of hours before her surgery. Before the surgery, I was really kind of curious. In the Olympics, of course, if somebody hasn't, one of the things that you deplete in a race like the marathon is your sodium, but it's easy to take in sodium and potassium. But one of the things we discovered in the LA Olympics was that you need calcium as well, and if you don't have calcium, your legs stop functioning. You can barely run, and that's what happened to a Swiss runner. They thought she was dying on her feet, but the reality was she just didn't have enough calcium in her system, and she couldn't get her muscles to work properly. So you need sodium, potassium chloride, and calcium. Normally we have enough calcium in our system so we don't have to worry about it. You don't have to take that much in. It's not like you need to chew on bones in order to get all that calcium that you need, or drink gallons and gallons of whole milk. You don't need to do that in order to get the calcium. We get it in a natural manner. After the release of the neurotransmitter in the synaptic cleft, the chemical migrates to the receiving neuron and attaches to transmitter receptors that either inhibit the potential of the receiving neuron or stimulate the neuron to reach its threshold, and so that it will fire. Much more neurotransmitters released in the synaptic cleft than can or will be used. Remember, we've got all this neurotransmitters flooding into the synaptic cleft. It's between 20 and 40 nanometers wide. So some of that neurotransmitter just kind of flows out. It's gone. So you need to release a select amount of it, and so you release more than you actually need. Getting rid of excess neurotransmitter in the synaptic cleft, since neurotransmitters are left in the cleft, it must be removed or it will continue to fire, and you certainly don't want that. You want to control the activity of the neurons. The amount of neurotransmitters detected by the autoreceptors, and it triggers a stop the release of the neurotransmitter. It's kind of like the shut-off valve on your as you're pumping gas. As soon as it detects fluid anywhere near the nozzle, it cuts off so it doesn't come shooting out of your gas tank. So it automatically shuts off, and that's what the autoreceptor is doing. It's telling the neurotransmitter stop pumping out neurotransmitter, and all it can do is shut it off. It doesn't take any back in. Removing excess neurotransmitters from the synaptic cleft is done in one of two ways. It's either done with an enzyme that enters the synaptic cleft and breaks it down, breaks down the excess neurotransmitter. This is what happens with acetylcholine. If we have too much acetylcholine in here, it will send an enzyme in there called acetylcholinesterase, and it breaks down the acetylcholine. The other way it does it is that it goes in and it takes it back into the neuron that was sending it out. It takes it back in, and this isn't called, it's called reuptake is what it's called. So when you have a chemical that blocks the reuptake of something, it's called a reuptake inhibitor. A good example of that would be Prozac. Prozac is a selective serotonin reuptake inhibitor. In other words, it inhibits the reuptake of serotonin. And that's all it inhibits. It doesn't inhibit anything else. It's an SSRI, it's selective serotonin reuptake inhibitor. Now the problem with Prozac is that it does increase the amount of serotonin. And serotonin can make you happy. But you've got other chemicals or neurotransmitters in your system that do different things. One of them is norepinephrine. Norepinephrine makes you feel like you can do things. Serotonin makes you feel happy, makes you feel better actually. So if you are increasing the serotonin level, but you're not increasing the norepinephrine level, as Prozac does, then you're making the person happier, but you're not increasing their feeling that they can get things, they can do things. This tends to increase their, it tends to block their inhibitions. And so they will do things. It's the way alcohol works. If you drink alcohol, one of the things that happens, all of a sudden you think you can dance. So you'll start dancing. Or you'll put a lampshade on your head and start around. You know, that's the old cartoon, put a lampshade on your head and start dancing around. Anyway, so the reuptake, it takes it back into the neuron that distributed it, and that's how it works. So you can either break it down with an enzyme, or you can take it back in to the cell. The neurotransmitter binds to the receptor molecule on the receiving neuron. Each neurotransmitter or ligand, and this is really kind of interesting because we're going to start talking about ligands. Well, ligands are just neurotransmitters, it's just another name for neurotransmitter. And the reason that it has two different names is because it was, these ideas were developed by two different disciplines. One was biology and the other was psychology. And since the two of them were talking, they were talking about the same thing, but they were using different words. So we can use these words interchangeably. We can either call them ligands or we can call them neurotransmitters. The ligand has different receptor molecules that they bind to called a ligand binding site. So if a cell is looking for serotonin, it has a chemical structure that will only allow serotonin to bind to it. If it's acetylcholine, of course, only acetylcholine can bind to it. But it gets kind of weird because chemical structures, sometimes a chemical structure will be similar, and so it will be able to bind to that ligand receptor site. And this is how drugs work. This is why you have a reaction when you smoke crystal meth. Crystal meth blocks the it's epinephrine. It blocks the epinephrine. Is that right? I think it's epinephrine. Blocks the epinephrine, so it allows you to feel excited for an extended, for a longer period of time. Caffeine works because it blocks the receptor site for adenosine, and adenosine is an inhibitory neurotransmitter that slows you down. So since it takes up that site, it can't slow you down, so you feel more excited. It's a substance known as adenosine. When an excitatory ligand is bound to the receptor molecule, it opens up sodium channels in the receptor molecule, allowing sodium to enter the neuron, of course. This is what we've been talking about for the last 30 minutes or so. If enough receptor molecules are stimulated by an excitatory ligand, the neuron's threshold will be reached and the neuron will respond with an electrical charge, yada, 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 same thing over and over again. If the neurotransmitter is inhibitory, it's an inhibitory ligand, it will open the chloride channels, of course, and it will make the neuron less likely to fire because it has a more negative charge than it did before. So it will take us even a stronger positive charge to get the thing to fire. Neurotransmitters are chemicals. And because they're chemicals, we can manipulate them. We can manipulate them with pharmaceuticals. While each receptor molecule binds exclusively to their neurotransmitter, there are similar chemicals that are structurally similar to the neurotransmitter that can bind to the receptor molecule as well. It's really kind of interesting how we discovered this. It's not that interesting, I guess. People poisoned themselves and they couldn't figure out what was happening. And then, of course, we broke down the chemicals. We started breaking down the chemicals in the 19th and 20th centuries. And what we discovered was that there were certain chemicals that acted as if they were neurotransmitters, or they blocked select neurotransmitters. Acetylcholine is an excitatory neurotransmitter with the poisons curare and bungarotoxin. Curare is from a South American plant, and bungarotoxin is from a snake on the island of Taiwan. It binds to the receptor molecule, causing paralysis. So acetylcholine, which makes you move, of course, if we have curare, if you have curare in your system, or you have bungarotoxin in your system, it inhabits the same receptor site as the acetylcholine, and since the acetylcholine allows you to move, the curare or the bungarotoxin is blocking that neuron, so you can't move at all. You're suddenly paralyzed. And of course, we actually use curare in surgery if we are trying to keep somebody from moving. A lot of times you'll have muscle spasms, but if we inject curare into their system, not enough to kill them, of course. If we inject curare into their system, they can't move that muscle. And of course, then we can do the surgery without worrying about a muscle spasm or a reaction. The curare kills you by arresting the muscles in your, paralyzing the muscles in your lungs so that you can't breathe. As I can imagine, that's not a very pleasant feeling. Acetylcholine receptor molecules are also the targets in the case of the poison muscarine from the Amanita muscaria mushroom. And this is what the Amanita muscarian mushroom looks like. As you can see, it's quite attractive. Don't eat it, it'll kill you. Muscarine, however, binds to the receptor molecule and mimics acetylcholine, causing the neuron to fire, resulting in spasms to seizures to death. So whereas curare inhabits the same, it is a antagonist, is that right? Yeah, it's an antagonist, so it blocks it. It keeps the acetylcholine from functioning, making you paralyzed. The muscarine overstimulates the same receptor site, and you start spasming, and then you have seizures, and then you die. So you get the opposite effect to curare from the Amanita mushroom. Chemicals that mimic neurotransmitters and cause a similar reaction are known as agonists. Ones that block it are known as antagonists. So you have an antagonist, the curare would be an antagonist, bungarotoxin would be an antagonist, and the Amanita mushroom would be an agonist. And of course, I can't go on the internet, so that doesn't matter. Acetylcholine molecule receptors are referred to as cholinergic. Acetylcholine has at least 4 functions and binds to at least 4 cholinergic receptors. Acetylcholine acts as a neuromuscular, in the neuromuscular system as an excitatory neurotransmitter, allows you to move. Acetylcholine acts on the vagus nerve and the heart muscle as an inhibitory neurotransmitter, so it slows down your heart, and it slows down, it slows down your heart muscle. Acetylcholine is used by the brain in the transfer of memory from short-term to long-term memory. And we already talked about the death of acetylcholine producing cells, causing the individual to have Alzheimer's disease or to lose, eventually lose their memory completely. It also is an inhibitory neurotransmitter that induces sleep, so it can put you into a coma as well. So that's acetylcholine. Acetylcholine shares some of its receptor sites with other chemicals, and for this reason the receptor sites are named after the alternate chemicals. This gets a little weird. For example, nicotine binds to the acetylcholine sites in the skeletal muscle and autonomic ganglia, and for that reason these sites are referred to as nicotinic cholinergic sites, receptor sites. They're nicotinic cholinergic because it binds to the same receptor site as acetylcholine. Muscarine cholinergic receptors also exist in the autonomic nervous system. Muscarine kills by stopping the heart and paralyzing the intestines. And of course, that is shocking. So that's how those poisons work. Nicotine is a poison. You can kill somebody with nicotine if you can give them enough of it. It will, the person will become paralyzed and die. And of course, they'll have a similar situation to what happens with the muscarine. There are two types of molecule receptors, ionotropic and metabotropic. Ionotropic receptors open ion channels and allow them to pass through. Ionotropic, this one is very rapid. The other is metabotropic. Metabotropic means change moving. Ionotropic means ion moving. These receptors activate molecules known as G proteins. It's a relatively slow process. So if you have a drug that is ionotropic, it acts very rapidly. If you have a drug that's metabotropic, it works very slowly. Your taste buds in your mouth are metabotropic for sugar. So if you eat something that's sweet, a lot of times it doesn't really register with you quite right away. You don't know exactly how sweet it is, and then all of a sudden it kind of hits you, oh, this is something that's sweet. However, the bitter receptors are ionotropic, and the reason is because you need to know bitter things, poisons are bitter, and for that reason you need to know to spit the stuff out as rapidly as possible. You certainly don't want to swallow it before you taste it. So bitter is ionotropic, sour is ionotropic, sweet is metabotropic. G proteins bind to the amino acid guanine in its many combinations. These guanine compounds may themselves open the ion channels or be part of a chain of reactions that open the ion channels. And for that reason, of course, this whole process is relatively slow as compared to the ionotropic, which is open it up right away. Open up the ion channels. There are 4 types of neuronal circuits. Neural chains are one of the types, positive feedback circuits, negative feedback circuits, and then oscillator circuits. The simplest neuronal circuit is a neural chain. A sensory neuron is activated by a stimulus, and it in turn activates a motor neuron that responds to the stimulus. In a positive feedback circuit, the effect is to increase an activity or to keep it going. In a negative feedback circuit, the effect is to stop an activity. In an oscillator circuit, the circuit serves as both a positive feedback circuit and a negative feedback circuit, depending on the circumstances, so it can oscillate between positive and negative. Most sensory neurons collect data, converge the input through a single neuron, and then diverge the signal when it arrives in the brain. This is how the eye works. Each moment of sight involves over 100 million receptor neurons that converge the information into the optic nerve, transmits it to the brain so that the signal can be diverged in various parts of the occipital lobe for interpretation. And this is how we understand things, is by, wait a minute, let me fix this. There we go. All right, I feel better. Anyway. Okay, so that's how the eye works. It takes in all this information. You've got 100 million different pieces of information, little bitty pixels of sight, and it sends it to different portions of the brain, and then it converges and gives you a single picture. And it does this every nanosecond. The electroencephalogram the Eeg is a device that reads the electrical impulses put off by the neuronal activity in the brain. EEGs are used to map brain functioning and can be used for sleep analysis or to monitor abnormal seizure activity. In case of a coma, the EEG will detect lack of activity, and that's what we're looking for. If you've ever seen the movie Flatliners, there's, of course, when we're trying to determine if somebody's alive or dead, we will attach a heart monitor, and it will tell us when we're getting an electrical impulse from the heart. We will attach an electrical monitor to the brain, an EEG, and that will tell us how much electrical activity is coming off the brain. If you've ever watched a television show where they were where somebody was dying, a lot of times both of those flatlined. In other words, they had no electrical activity coming off their heart or off their brain, which meant that they were dead because they had no brain activity. Normally, even when you're asleep, you have brain activity. It's one of the reasons why we talk about delta wave sleep and theta wave sleep and alpha waves and beta waves and whatnot. So when we're awake, we have beta waves. When we're asleep, we go into delta wave sleep. Delta is a big triangular shaped structure. That's what the wave looks like. Beta waves are little bitty guys. Anyway, EEGs. 30 million people worldwide suffer from epilepsy. I know there's nobody here.
In class started like 10 minutes early.
Is it? What time is it?
I thought I had time.
You have time. You have
9:49.
Yeah, you have lots of time.
Okay.
Okay, I'm talking to the people in television land.
I thought I didn't get an email and I kind of got scared.
Why?
Don't come to class. I'll just send it out. I thought that's what you're doing.
Oh, no, my goodness. I never get sick. My daughter's sick, but I'm not sick. Of course, she's 1,500 miles away. So we're talking about epilepsy. As you can see, Scott's not here and Earlson's not here, so usually they're in this classroom. 30 million people worldwide suffer from epilepsy. Epilepsy is characterized by seizures. Seizures are involuntary synchronized excitation of large groups of nerve cells in the brain. It's kind of like a lightning storm in your brain where it just hits, and of course you can't function because you've got a portion of your brain that's shorting out at that point. Seizures can be triggered by trauma or injury to the brain. We see this with traumatic brain injury. Sometimes they will have epileptic-like symptoms. It can be from chemical changes derived from metabolic faults in your system. Can be caused by exposure to toxins, can cause epilepsy. It can be caused by mutations in ion channels. Usually if this is the case or this is the case, then the individual will have epilepsy from birth. And of course, some individuals, their brains will fire. Their brains will just fire and they will have epilepsy. There's not a whole lot we can do about it. Yes, there is. We can give them medication that stops that stuff.
Is that the same as when people see like flashing lights? Is that the same thing?
Usually not. Well, actually, a petite mal is kind of flashing lights.
Mm.
Okay. But flashing lights can have to do with your optic nerve. It can be your retina detaching from the back of your eyeball, which sounds horrible,
Yeah.
but it doesn't really make that much difference. My wife has detached retinas, but she can see fine.
Oh.
Yeah, I know. It's kind of exciting. It happened when she was in the service. She was flying a lot, and the changes of pressure caused her, I guess she has delicate eyeballs or something, I don't know. Anyway, she had that problem when she was in the service. So if you have mutations in your ion channels, or you have chemical changes derived from metabolic faults, this will cause epilepsy from birth. If you have this kind of a situation, we can control it with medication. We have anti-seizure medication.
I didn't know that.
Carbamazepine is one of them. Tegretol is another one. Well, anyway, and there's new ones. Those are the old ones. When I was working in medicine, we had Tegretol and carbamazepine. Epilepsy is characterized by various types of seizures. Grand mal seizures are the most extreme form of epilepsy. Grand mal seizures are characterized by total muscle contraction, followed by alternate jerking and relaxation. The seizures normally only last 1 to 2 minutes, but recovery can take as long as several hours. So somebody will have a seizure, and then could take them the rest of the day to recover from their seizure. Petit mal seizures are characterized by losses of awareness of from 5 to 15 seconds, and sometimes you'll have flashes of light, is what you see. It's really kind of interesting when people start having seizures. A lot of times they'll smell something, or they will see a halo, or they will taste horrible tastes, as interesting as that is. Sometimes when people have migraine headaches, they'll see a halo, start seeing halos, which means I'm about to have a migraine headache. When I was up in the Andes, we were up 15,000 feet. Is that how high we were? We were pretty high, up in the Andes. And they said that you're going to have an oxygen debt. And the only thing that I noticed was that I started seeing halos. I wasn't reacting to things like, I wasn't reacting normally to things because there was not nearly as much oxygen that high. So we were in Cusco. We were going to Machu Picchu up in the Andes. Anyway, that's the only reaction I've ever had. And it only lasted for about 10 or 15 minutes. After that, everything was fine. Complex partial seizures do not involve the entire brain. The individual may experience an aura, a perceived sensation that precedes the seizure. A lot of times they're negative auras. They smell bad smells, or usually smells like rotten eggs, or they'll taste something horrible in their mouth. I'm not going to tell you what they usually say it tastes like, but you can imagine. Okay, bad tastes. Certain personality traits often accompany complex partial seizures, but it is not certain whether the traits are triggered by the seizures or the seizures are triggered by the traits. So we're not exactly sure. People will change their personalities. A lot of individuals, if you've been around them a long time, you know when they're about to have an epileptic seizure. They become easily aggravated. They're very difficult to get along with, and then they'll have a seizure. Normally they don't act that way, so it's a tell for those select individuals that they're about to have a seizure. And of course, this is an individual who's having a seizure. You can see there's extreme activity in select portions of their brain. This is the frontal lobe. So you can see they're having seizures in that portion of the brain. There have been individuals that have seizures almost continually. Those individuals, normally it's only on one side of the brain, and normally it's on the left side of the brain, as you can see on this individual. This is a normal person, and this is a person with having seizures. So what we can do is, since it's in one portion of the brain, just one half of the brain, we can actually take that portion of the brain out. We can take out half of somebody, we can do what they call a hemispherectomy, and take that whole half of the brain out.
Oh, yeah.
Okay, and then they won't have any seizures anymore because the seizures are all on one side.
But it's better if the person's younger, right?
Well, we can't do it if they're over the age of 12. But normally, epilepsy is something that you're born with.
Mhm.
So we know that they are prone to epilepsy. Of course, if they have a TBI, they have, if it's induced by a toxin, if it's induced by a blow to the head, then there's not a whole lot we can do about it. But if they're young enough and they have their seizures are severe enough, we can just take out half the brain. Their intellectual functioning is the same. There are some motor movements that they can't do, but other than that, they are normal. And this is the only way they can be normal. Now, sadly enough, you can induce epilepsy by taking medications, certain medications, certain pharmaceuticals. One of those pharmaceuticals is LSD, lysergic acid diethylmine. Another one, some people have had serious reactions to marijuana. But these are individuals that tend to have other problems as well before they go into this. Anyway, that's the way it works. Yeah, marijuana cure everybody's ills. Unfortunately, it doesn't always work that way. So how much time do I have? What time is it?
Mhm.
Oh, wait a minute, I got it right here. 9:58, okay, so I got about 20 minutes. All right, so let's go into chapter 4. I'll go ahead and do it. Oh, psychopharmacology. We'll talk about drugs and behavior. That ought to be fun. Okay.
Oh,
Yes,
I'm way too early, huh?
yeah, you're
Yeah, it's
about 30 minutes early.
Okay.
Okay, so this chapter is about psychopharmacology. Psychopharmacology is the pharmacy of the brain. We're going to talk about select neurotransmitters, certain drugs, and how they change your behavior. This is a really fun chapter. Ashford University, I wonder what it says there. Most drugs affect the brain and behavior by changing synaptic transmission. Axons release a chemical that either excites or inhibits the attached neuron. This is called a neurotransmitter or merely a transmitter. So we're talking about chemicals here in the brain. The first transmitters to be discovered were the amine transmitters in the 1940s. Acetylcholine was one of them, norepinephrine, and epinephrine. Epinephrine has two names, as odd as that may seem. So does norepinephrine. Epinephrine has another name of adrenaline. So, okay, so don't get them mixed up. They're the same thing. And norepinephrine, of course, at the same time. In the 1950s, the amino acid transmitters were discovered: glutamate, glycine, gamma-aminobutyric acid, GABA. This controls movement, this controls memory, this controls feelings of well-being. The glutamates are all inhibitory. GABA, we discovered that if we increase GABA in somebody's brain, that it will take away anxiety, as odd as that seems. So the individuals who are overly anxious, who seem to be scared of everything, we can increase their GABA level, we can cure them of their problem, we can make them less anxious. In the 1970s, investigators recognized that this is the 1970s. Now, I know that you were born like last week, and all of this seems like ancient history, but the reality is all of this has happened since I was born. So when I first went to high school, when I first went away to college, and started studying this stuff, the only neurotransmitters we actually knew, the only neurotransmitters we actually knew were these in the 1940s and 1950s, because I was going to school in the 1960s and 1970s. And it wasn't until the 1970s that we started discovering other things. So you can imagine what an abnormal psychology book looked like in the 1970s. My abnormal psychology from my master's degree. None of this stuff a lot of this stuff hadn't been discovered yet. We didn't know what serotonin was. We didn't know where depression came from. We were confused. In the 1970s, investigators recognized that short chains of amino acids called peptides also served as transmitters, endogenous opioids from inside. In other words, endorphins. We didn't even know what endorphins, dynorphins, or enkephalins were. Oxytocin was something brand new that we just discovered. Substance P has to do with pain. Oxytocin has to do with the nesting. It's a nesting hormone. It makes if you're pregnant, it makes the milk drop into your breasts so that you can lactate, so that you can feed your baby. Substance B has to do with pain. Vasopressin has to do with urinating. As weird as that seems, it's the antidiuretic hormone, vasopressin. So now we can control whether you urinate or not. Is this important? It sure is to kids that wet the bed, because can't control this. And then we realized, looking at this stuff, then we realized that the reason that they wet the bed was because they didn't have as much of this stuff in their system. And it's genetic. So there would be whole families of bedwetters. And now, of course, we can control that if we care to with vasopressin. Transmitters must meet the following criteria. The chemical exists in the presynaptic terminal. In other words, that's where it is. This is how we discovered Viagra, as bizarre as that may seem. Viagra has to do with nitrous oxide. Nitrous oxide, we didn't realize it was a neurotransmitter until the 1990s. So once we discovered nitrous oxide as a neurotransmitter, then we realized that the whole reason that males get an erection has to do with nitrous oxide. So if we can control the nitrous oxide, now all of a sudden we can allow them to have an erection where they didn't have it before. This is what erectile dysfunction is all about. The other thing was marijuana. Marijuana messed people up, and we didn't have a clue what was going on. And people were saying, dude, it's all natural. You know, we have natural receptor sites. I mean, humans have been like smoking pot for like forever, man. And the reality was, of course, that wasn't true at all. It had to do with hunger. It inhabits the same receptor site as a neurotransmitter that tells us that we're hungry. And because of that, of course, it makes you hungry. That's why people get the munchies after they smoke marijuana. Okay, so all of this, here we're dealing with two different chemicals, but there was already a receptor site for that other chemical. So the chemical must exist in the presynaptic terminal. The transmitter is manufactured in the neuron. The transmitter is released when the neuron fires. Specific receptors exist to receive the transmitter. Adequate amounts of the transmitter will make the neuron fire. Blocking the transmitter stops activity. These are the things that have to be there in order for it to be a neurotransmitter. I can't go online, so we can't talk about that. There are two types of receptors. There are rapid receptors, ionotropic, and there are slow receptors, metabotropic. Ionotropic receptors respond immediately and allow ions to pass through the receptor when the transmitter is present, and because of that, of course, the chemicals transfer very rapidly from one place to the other. Metabotropic have to do with releasing the G protein. It activates an ion chemical chain that opens up the ion channel, and it changes the cell. This one is very slow, and this one is very fast. What's the difference? Well, if you ate something that was poison, like if you bit into some pharmaceutical, bite into an aspirin sometime, you would taste it almost immediately. Why? Because it's ionotropic. So you would taste it very rapidly. However, what if you bit into an apple and you needed to decide whether it was sour or sweet? Well, it's going to take you chewing a little bit before you realize, oh, this is a sweet apple, it's not a sour apple. And the reason is because The sweet flavor is metabotropic. Bitter flavors are ionotropic. Okay, so that's very rapid. The reason is because sweet things are good for you, and since it's good for you, it can stay in your mouth for an extended length of time. Poison things are bitter. You need to know right away so you can spit them out. Okay, that makes sense. Acetylcholine was the first neurotransmitter that was discovered. Acetylcholine is contained in cholinergic nerve cells. The nucleus basalis and the medial septal nucleus in the basal forebrain are cholinergic cells that project to the hippocampus and amygdala to promote memory. Okay, then, so that's why you remember things. If we can excite your brain, then we can get you to remember things. So we try to use humor. Humor works. If we can get you excited about something, we get your adrenaline pumping, then we can get you to remember things. Cells in this area are often destroyed in Alzheimer's disease, and that's the reason that they have memory problems. The drugs atropine, used to dilate your eyes, and scopolamine, which is also known as the truth serum, are both acetylcholine antagonists. They block the action of acetylcholine. And for that reason, scopolamine, if somebody's ever given you scopolamine, you can't tell a lie. Alcohol allows you to tell all the lies you want, but scopolamine actually won't allow you to tell a lie. If they put atropine drops in your eyes, then your eyes will dilate and you can't make them smaller. You've lost the control over your iris, so your eyes are pretty big. Okay. Women used to, when a woman sees a man and she's excited by him, she's attracted to him, her eyes will dilate. So back in the day, women used to put stuff in their eyes to make their pupils larger. They put poisons in their eyes.
Oh my God.
They put belladonna in their eyes in order to make their eyes dilated. And so men, when they would see them, they would think, oh, geez, she really likes me. Her eyes are dilated. But it was a trick. Yeah, I know, it was a chemical trick. As stupid as that is. The pedunculopontine nucleus and the laterodorsal tegmental nucleus control sleep and are cholinergic cells. So acetylcholine controls your sleep. There are two main types of acetylcholine receptors, nicotinic and muscarinic, and both of these are poisons. Nicotine is a poison, and muscarine is a amanita muscarine mushroom is a poisonous mushroom. Nicotinic receptors are ionotropic and have excitatory functions. Muscarinic receptors are metabotropic and can be excitatory or inhibitory. There are 5 transmitters classified as monoamines in 2 groups. Catecholamines are norepinephrine, epinephrine, and dopamine are catecholamines, and the endolamines are serotonin and melatonin. Serotonin makes you happy and melatonin puts you to sleep. So we have catecholamines and endolamines. How much time do I have? Okay. Dopamine is one of the most abundant transmitters in your brain. It's found all over the brain, but 2 of the most important areas are the mesostriatal system and the mesolimbocortical system. And those are the 2 systems right there. It's right in the front of your brain. The mesostriatal system, this system includes the substantia nigra to the striatum caudate and the putamen. That's the part in the back. That's this part right here. That's your basal ganglia. This area of the brain does not actually have very many nerve cells, so what nerves are there can control thousands of different synapses. Degeneration of the system can result in Parkinson's disease. If you've ever been around somebody with Parkinson's disease, they can't control themselves. Their hands are always shaking. They walk in a shuffling manner. They lose their ability to move. So this area, the basal ganglia, has to do with motor movement. This can be caused by aging or in select individuals. It can be caused by drug use or frequent and prolonged head trauma to boxers. This is what happened to Muhammad Ali. Muhammad Ali had Parkinson's disease, and it was induced by the fact that he was a boxer. He got punched in the head a lot. You can do the same thing with crystal meth. Crystal meth will do this to you. You get the jerks, you get the shakes. It's called the meth dance. It's kind of fun. We're not. Anyway, that's the areas we were talking about. There's your substantia nigra is the black one. And the other one is your raphe nuclei. The mesolimbocortical system, this area is just in front of the mesostriatal system, or the area. This area projects into the limbic system, the amygdala, the hippocampus, nucleus accumbens. All these have to do with emotions and memory. Overstimulation of this area in the dopamine pathways seem to cause schizophrenia. Oh, great. So if it's in this area, if it's in the mesostriatal area, you get Parkinson's disease. And if you get overstimulation of dopamine in the mesolimbic cortical system, then you get schizophrenia.
That's if you have too much dopamine in that.
Yeah, too many dopamine receptor sites. But the dopamine receptor sites we're talking about are D2 sites. 5 types of dopamine receptors have been identified from 1 to 5, D1, D2, D3, D4, D5. D1 and D5 react in similar manners, but are very much different from D2, D3, and D4 sites. Antipsychotic drugs that bind D2 receptor sites relieve the symptoms of schizophrenia. So we didn't really know how to control schizophrenia until we developed these drugs that could control D2 receptor sites. Norepinephrine or noradrenaline is released from 3 different areas of the brainstem. The impact of the neurons producing norepinephrine expands broadly throughout the cerebrum, the cerebellum, and the spinal cord. This transmitter is believed to affect a broad range of behavioral and physiological functions. It gives you a feeling of well-being, norepinephrine, and that's a good feeling. Okay. Serotonin is classified as an endolamine, a subclassification of monoamines. Large areas of the brain are controlled by serotonin-producing neurons. Few neurons actually release serotonin. The main grouping is in an area of the brainstem called the raphe nuclei, and it's right here. 15 types of serotonin receptors have been identified. So serotonin, when we talk about serotonin, we usually talk about depression, but the reality is that serotonin controls your desires to, it does control your sexual desires to some extent, but it also controls your hunger. People that are alcoholics, serotonin controls that. Potentially if we can give you Prozac, it'll take your desire to drink so much, potentially, as strange as that may seem. Amino acids as transmitters, some amino acids are transmitters. Excitatory amino acids, glutamate and aspartate. Glutamate is the most common excitatory transmitter. Inhibitory amino acids, gamma-aminobutyric acid. The most common inhibitory neurotransmitter is GABA and then glycine. And of course, GABA has to do with anxiety. If we can increase your GABA level, then the probability that you'll be overly anxious is not very high. Glutamate uses both ionotropic and receptors and metabotropic receptors. The ionotropic receptors are AMPA receptors. AMPA receptors are able to increase with learning, accelerating the processing function. Kainate receptors are another type of ionotropic receptor, and NMDA receptors. This is involved in information processing, NMDA. Glutamate has a feature known as excitotoxicity, whereby a neuron that is depolarized due to injury or stroke will die. Glutamate is cleared by astrocytes or glial cells. Astrocytes are glial cells that clean up your brain. And of course, this is what happens as you get older. Of course, I'm 70 years old, so I've got all kinds of neurons dying in my brain. And so I need all the astrocytes I can get to clean this out. If it clogs things up, if my astrocytes stop functioning, then I'll get Alzheimer's disease. And I certainly don't want to do that. GABA receptors can be divided into three types, A, B, and C. GABA-A receptors contain chloride channels and are ionotropic. GABA-B receptors are metabotropic. GABA-C receptors are ionotropic with chloride channels, but they have different function than the GABA-A receptors. Drugs that block the actions of GABA can cause seizures. So you need a select amount of GABA in your system. If you don't have enough GABA in your system, you become overly anxious. But if it blocks it too much, then you'll start having seizures, and that ain't good. Sometimes when people take drugs, a lot of times when people take drugs, they really don't know what's going on in their brains, and they're causing a lot of damage, and they'll just, weird things will happen to them. They'll smoke pot the first time and they'll become schizophrenic. It changes the chemical structure of your brain. So these are really kind of dangerous, taking all these stupid drugs, just because, all your girlfriends or all your boyfriends can do this stuff doesn't mean that you can do it. Sometimes you take drugs one time and you're gone forever.
Yeah.
You just blowed your brains out because of GABA and seizures or whatever, schizophrenia. Come on in. I'm going to stop in a minute, so I'll probably do one more slide. Peptides. Many peptides have prominent roles in the brain as neurotransmitters. Opioid peptides, endorphins, enkephalins, and dynorphins. So it's not just endorphins. People talk about, runner's high, man. I had all these endorphins running through your system. Well, there's three different types. And they're right, opioids and endorphins are connected to each other. Opioids do not work on me. I cannot take drugs. I cannot take an opiate or an opioid to take away pain. It doesn't work for me, which pisses doctors off because they want everybody to be exactly the same. Substance B, cholecystokinin, neurotensin, neuropeptide Y are found in your gut and your spinal column. Substance P tells you when you're in pain. Cholecystokinin is kind of interesting. It comes out of your gallbladder, and it has to do with a lot of different things. One of them has to do with memory, but it also has to do with, tells you when you're hungry or when you're not. Pituitary hormones, oxytocin, and vasopressin, of course. And let me stop this thing since it is time. So much fun stuff. Aren't we having a good time yet? Okay.